if you've never used Insightmaker before, it's a new thing. The way we're going to go through this today is I'm going to present a scenario which I've used in the past um, prior to sort of my integration of Insightmaker into my course, and think about like how a student interacts with a certain scenario without Insightmaker first, and then we'll see it worked out with Insightmaker. So here's my scenario, and so this is based on um, I'm sure at the end slides will be available to us. I'm gonna try this one more time. Um, where is my chat? Chat. Let's stick this link in the chat. So this is actually the source article for this scenario. It's about traffic flow using the Laplace transform. So this is something that's going to come clearly after we've introduced the Laplace transform, but instead of cars following each other, we have three cyclists riding in a single file line. The lead rider does whatever they want. So in this scenario, they briefly accelerate and then stop accelerating. The goal of the two riders following this lead rider is to match the speed of the rider that's directly in front of them. They achieve this by accelerating at a rate proportional to the difference between their velocity and the velocity of the rider in front of them. The thing that makes the problem really interesting is that there's some positive reaction time, because people or things do not actually react instantaneously to a difference in velocity. I made the reaction time 0.2 seconds. So what's going on is when a rider in front of you accelerates, you react by accelerating at a rate proportional to the difference between their velocity and your velocity, but those velocities are 0.2 seconds earlier. And just as a part of the scenario, you say that the two following riders are identical. In the scenario that I present to my students, we say that the riders are in fact identical twins, and there are some identical twins in the professional cycling world. So there's, it's these are things that I put into the scenario. So there's one constant of proportionality. And so the kind of setup is to set up some differential equations, and the ones that we get are these. So we've got the position functions are xi of t, and so we get xi double prime is c, this constant of proportionality, times, so the h is the Heaviside step function, and so this institutes the delay. So we have shifted step functions, and so this is the difference between the two velocities 0.2 seconds ago, essentially. And so this is for riders 2 and 3. Rider 1, we have this as his acceleration function. So it's h of t minus h of t minus 0.2. So essentially, this is saying that the lead rider accelerates at a rate of 1 meter per second squared for 0.2 of a second, and then stops accelerating. And so the question that we present to the students is what's going to happen to the riders behind, depending on what the value of this constant c is. So this is where, we're presenting this scenario kind of analytically, and just, for the purposes of talking about how Insightmaker is useful, we're going to go through sort of briefly how one solves this problem analytically. This is in the original, basically the solution presented in the original source paper. And so what we have to do with some algebra and some other tricks is derive a recursive formula for the Laplace transforms of these cyclists of their acceleration functions. And one of the steps is you have to, instead of considering the position functions, consider the difference between the position functions and their tangent line approximations at 0. That way you get to zero out the initial conditions in the Laplace transforms, which, when you teach this material, you say, it's kind of a perpetual headache of having non-zero initial conditions in Laplace transform problems. So you get rid of that, then you do some algebra, and you get this nice little recursive formula, which then you can relate everything to the acceleration function of the original writer, where the second writer has this a2 of s as the transform of their acceleration function, and the third writer has the second one. And then we kind of say, okay, this is when students have some reasonable experience with the Laplace transform. We notice that in the third writer's transform, there's a square in the denominator, and we start talking about qualitative analysis of the Laplace transform. We focus on this c plus se to the 0.2s, and we want to know about the zeros of that function. The students are presented with the following table, which says this. Kind of briefly, so if c is less than or equal to 5 over e, the poles of these Laplace transforms have a negative real part and no imaginary part. This means, so the thing that I want the students to come away with is make all of these conclusions based on their knowledge of the Laplace transform. So in that case, acceleration functions approach 0 for both writers. It's kind of like a overdamped oscillator, but obviously it's not. If c is between 5 over e and 5 pi over 2, now there's a negative real part and a positive or a non-zero imaginary part. So there's oscillation. And then if c is 5 pi over 2, that's where a bifurcation happens, where suddenly the real part becomes positive. And so that you have oscillations of growing amplitude. And because of the multiplicity of the poles in the third writers, that gets essentially in the time domain, you get a multiplication by t. So the oscillations grow more rapidly. And so in the case when c is greater than 5 pi over 2, inevitably a collision between writers is going to happen. Okay, so that was obviously very fast because probably most of you are familiar with theory of Laplace transforms. And here's just if you can imagine how students might react to going through all of this. And this might take a couple days for the students, where there's plenty of algebra. We're walking through a lot of how the theory of the qualitative theory of Laplace transforms works, and we get to how a student might react. And so it's something like this. And I've, gotten very, isomorphic to this reaction. What are we doing here? And so I tell the students and they go, oh. And then the reaction is, okay, so just what do you want me to write as my final answer? If this is how the student is reacting to working through a modeling scenario where they're kind of not getting the punchline, something about this modeling scenario isn't working. Somehow modeling as the way of teaching differential equations is, it's supposed to enforce something, not confuse the student. So now I'm going to say, well, how can software help this? And specifically, it's going to be Insightmaker. And I have many other at the end, I'll give a link to the Insightmaker text that I've put up. So it's a pretext text, so that it's a little plug for Oscar's talk next. So right now we're going to say, okay, let's go to insightmaker.com, and I am going to take my link to this insight, and I'm going to put that in the chat as well here. Chat. And we're going to follow along through this. I'm going to stop sharing that and share Insightmaker. So Insightmaker uses stock flow modeling or compartmental modeling to build differential equations. And so, and I'm using one of the features, which is storytelling in Insightmaker, to build this. So the first thing we do is create a stock flow diagram for the first rider. So the flow is so these rectangular items are called stocks. Those are roughly dependent variables in the model. They depend on time. The sum of all the flows is the time derivative of that stock. And so essentially we have the derivative of velocity is acceleration, the derivative of velocity of position is velocity, and the acceleration function here is step 0.1 minus step 0.2 of 1. This is how I'm just building that step Heaviside step function. This is the control of the first rider. Then what we can do is build a system of differential equations, essentially by duplicating this rider, the first rider. So each one of these we have a duplicate, and there's sort of theory on how you glue diagrams together, but with some experience with Insightmaker, these make sense. I have the students build this themselves because I use Insightmaker throughout the semester. This might be coming in week 11 or 12 of a 14-week semester. So students are pretty experienced with building these diagrams to model, to describe differential equations in the class. Our flows for the acceleration functions for velocity riders 2 and 3 use this built-in delay function in Insightmaker. Insightmaker has tons of cool built-in functions. The delay is the delay, it gives us a delay on this differential equation. So then we can actually start running the model, running the simulation, and ask a few of these questions. So we can build a slider for C. So C has a slider on it. Right now it's 1, and then we can just see how the system behaves as we change C. So right now, I'm actually going to stop the story, and I'm going to say, so open up the slider, and I'm going to say simulate. So right now, this gives me how the solutions behave when C equals 1. And one of the things that I'm even going to point out with this is when the students look at this, some of them initially look at this and say, so the first thing that happens is rider 1's velocity increases for 0.2 of a second and then stops changing. One of the first things that some of the students this last semester said is, well, wait, I think my insight is wrong because the velocity of rider 2 and 3 doesn't change initially. And then I say, well, can you think about why those two don't change until time is 0.2? And then they say, oh, it's because there was a delay. So somehow when you were just doing this analytically without being able to see a simulation, the fact what a delay in reaction is for a lot of the students wasn't even registering. And then we start saying, okay, what happens when we change C? Well, we've got the sliders linked up here. So if I start changing C, we can just change it up to 1.5. It changed a little. So 5 over E is about 1.85-ish. If I change up to 1.85, it's not obvious that there's a little bit of sinusoidal action going on here. If you change the configuration to the tabular output, you can actually see that the first rider actually goes a little bit above the equilibrium solution and then decreases back down to it. I'm gonna not do that right now because if we change that C up a little bit higher, now we actually see that sinusoidal action happening. And so that change happens at 5 over E, which is actually sort of magical that when you see that happening, and then you say, okay, so now what's going to happen as we go further? Now we see, oh, we've got these oscillations in the velocity, and what students are able to see now is that, oh, basically the riders are out accelerating their reaction time to some degree. But they react too violently and then they have to slow down violently. And then if you start ramping it up, it turns out that 5 pi over, oh God, now I need to remember what that bifurcation value actually was. It was 5 pi over 2. And if we 5 pi over 2-ish, so that's somewhere in the 7.8, right? What we're seeing now is, okay, the amplitude increases, but then it starts decreasing again. If we pass 5 pi over 2, I'm going to go up to 8. Okay, now the oscillations, so oscillations for rider 3 in their velocity are growing without bound. We can see that a collision is going to occur. Now the students are going to be able to see, like, they can just see what's happening and say, why is that happening? So finally, I can kind of go back to what you want students to be getting out of this is something like this. So when C is small, the reactions aren't so violent. After the first rider settles down, the riders following just kind of catch up. If C is moderate, the riders react a little too much, but then they need to slow down and then they need to speed up, but it still settles down. If C is too large, the acceleration is too violent for their own reaction times. A collision becomes inevitable. What students can do, so now I have them work through the insight before they actually go through the analysis. Now they know what's supposed to happen, they work through the analysis, and then they can actually appreciate, like, oh, the analytic methods actually predict more, they give these 5 over E and 5 pi over 2 that they just estimated with the insight previously. So now I'm gonna kind of open it up to questions. The last thing I'm gonna do is I'm gonna open that up, just put this into the chat as well. So this is the pretext book that I use to get students basically up to snuff on using Insightmaker in there to do differential equations. And I think I did not actually, I was not just sharing the PDF, the last one. So this is kind of, these are what I want students to have after they go through the insight and then do the analysis. And so in the pretext book, there's a bunch more scenarios of kind of how you can have students working with Insightmaker to better understand some of the theory that they're encountering.